Hello, this presentation is about basic utility vehicle dashboard display, motivating computing and engineering undergraduate research from University of Wisconsin-Oshkosh, Fox City campus. My name is Ray, and these are 4 authors for this project. Here is a picture of the basic utility vehicle. The BUV was built by Fox Engineering Society, and it was modeled after an electric golf cart. Students from Fox Bytes Computer Science Club designed a dashboard display for it. Electric vehicles are seen as the future of clean transportation. The BUV concept was created for university campuses and other such institutions or organizations to partner with undeveloped communities to help with their transportation needs. Building an BUV is a perfect way to provide undergraduate engineering and technology students with a practical, cutting-edge project that also illustrates and teaches several scientific and engineering principles. With the current pace of technology, the demand for skilled workers is only going to increase. So it is crucial to increase the number of students in areas such as computer science, engineering, and technology. The present work introduces an overall BUV project, discusses the design approach for the dashboard display, details the process by which the software was developed and integrated into the hardware, and presents some lessons learned. Also, when you are driving, you always want to know the information of your vehicle. We found 2 ways to display vehicle information. One is to buy different kinds of sensors and collect the data for display. Raspberry Pi would be used for this option. The display would show the speed, temperature, motor speed, which is RPM, battery capacity, distance traveled, and so on. Too many sensors and wires are required with this option, and it has no much educational significance for students, since it is only needed to connect wires and produce simple coding. The other option is connecting the display with the motor controller that is used to control the current and signal to the electric motor. Based on the affordable technologies and devices that are used for building BUV, the easiest way to create an accurate dashboard is to connect it directly with the Ultrax controller that's used for the vehicle. Since the Ultrax Toolkit software has all the information that was needed, and it only works on a Windows operating system, Windows was loaded on a Pi, and the software was installed. But the Pi proved to be unable to handle Windows in a practical manner. The students tried to obtain the application programming interface, which could allow one to bypass the Windows operating system. However, it was not possible to obtain the API because Ultrax company owns property rights for their invention. Running Toolkit on the tablet would allow data to be obtained from the motor controller, and another control application would collect and display the data in a suitable format. However, a lot of memory is required for this, so a laptop was purchased for this project. The laptop must be mounted on the vehicle close to the steering wheel in order to replicate the experience that a normal vehicle would provide. So the laptop is flipped backward to use as a monitor. A customer plastic case was designed in a SolidWorks and 3D printed to house the display and protect it. Also, we considered power supply for the laptop. The display was powered by connecting to the main vehicle, which has a 48-volt battery bank via a adapter. It also connected to the motor controller via a USB-A to USB-B cable. Software design. C# and the Windows Forms library were used for front-end development. After Excel files proved to be too slow, text files were used. Furthermore, several members of the team had some experience in developing graphic user interface, which is GUI, in the form of applications. It was easy to develop the basic layout of the GUI. Steering arrays with a capacity of 48 elements were used. Real data was separated by commas, so the process were relatively straightforward. The file was read every quarter of a second and the values represented were labeled. The team can get some data from the controller and calculate the rest from existing data. A virtual button on the toolkit GUI had to be manually pressed every time new data was needed. To automate the process, the control program accessed the data via a button press every 250 milliseconds, which is a quarter second. The button was programmed to be pressed automatically and was hidden from the user to avoid confusion. Thus, a fresh set of results was obtained from toolkit every quarter second. A form closing event was used to save distance and energy usage in the separate text file when the application was closed. The application then referred to these values when it was restarted. After running the application connected to the BUV, adjustments to the display font size and layout were made. Debugging of the software was done, especially the hidden button press. Performance and design modification. At the end, the prototype display was connected and worked fine. The updating frequency of 4 Hz, which is quarter second, worked well. The data was expected to be more accurate than using external sensors, as this was pulled directly from the motor controller. The students will continue to refine and improve the display, including the type of information that is shown and possibly displaying some of it graphically. So, code can be improved to be more reliable. Automatic starting is something we also want to do. At this moment, we have to set path on Ultrax toolkit every time we use it. So we hope to have automatic connected to Ultrax toolkit in the future. This paper details the design and development of a dashboard-style display for the BUV being built at the University of Wisconsin OSHKOSH Fox City campus. A lot of people, as listed, helped with this project. I'm really grateful to those who contribute to this project. Thank you again. Thank you for helping. Finally, I would like to thank you for watching my presentation.